All right, section 9-4 is on reduction formulas. The objective of this section is given an integral involving a power of a trig function. Use a reduction formula to evaluate the integral. So we're talking about powers of trig functions that we're working with and finding a reduction formula for that. So let's first start out with what a reduction formula is. A reduction formula is an equation expressing an integral of a function to some power. And again, for all of ours, we're going to be working with powers of trig functions in this section. It's expressing an integral of a function to some power in terms of an integral of the same function, but to a smaller power. This is why we call it a reduction formula, because you're reducing it from some function raised to the 10th power, for example, that you're integrating, to now that same function raised to the 9th power, maybe the 8th power, whatever the case may be. So it's a reduction formula. You're reducing the power on that integral each time. And eventually you get it down to a small enough integral that you can deal with it and actually integrate it. One thing to note here, many reduction formulas are derived directly from the integration by parts. That's where our properties are that we're going to work with today. All right, one thing to recall here for us, this goes back a few chapters for us, but we learned the integrals of your trig functions, and here they are all listed. So the integral of sine is a negative cosine of x plus c. The integral of tangent is equal to the natural log of the absolute value of secant of x plus c. And the integral of secant of x is equal to the natural log of the absolute value of secant of x plus tangent of x plus c. Now again, once you know the three properties that we just went through over here on the left, there's a nice little property that tells us how to get the ones on the right. If you replace each of the trig functions there with the cofunction, and then just take the opposite of your answer, you get those three properties on the right. And actually I have a note here to remind us of that, I guess, that this is basically written out that same thing I just described there. To find the integrals of the cofunctions there in the right column, replace each trig function in the left column with its cofunction, and take the opposite of the result. And we saw that same property hold up when we were talking about derivatives of your trig functions, derivatives of your inverse trig functions. We also saw it here with the integrals of your trig functions. All right, we're going to use those throughout this section here because of the fact that we're talking about integrals of powers of trig functions. So that's why we just wanted to recall what those definitions were there. All right, let's start with an example here to kind of illustrate how you come up with a reduction formula. And I'm going to use just another type of function. We could certainly use one of our integrals of a power of a trig function, but I'm going to go with just a simpler example here really to start off with. So here we've got the integral of x to the nth times e to the x. So it's the x to the nth part that I'm focusing on here, and I want to reduce the power on it. Eventually I want this thing to go all the way down to x to the 0. It's just a constant, and then I can integrate just e to the x. But let's write down what the reduction formula would be. Again, these are mostly derived from integration by parts. I'm going to use this rapid repeated technique, although I only need to do one iteration of this to actually get the rule here. But I'll still use this rapid repeated technique. I'm going to let x to the nth be the u column, and that means e to the x is the dv column. So the derivative of x to the nth is going to be n times x to the n minus 1. And the integral of the dv column is e to the x. And actually that's as far as I need to go. Again, one iteration here is all that we need to do. So we're going to multiply that diagonal. We're going to integrate this bottom row here. Remember your sign alternates, plus and minus. So our reduction formula looks like this for this function. I'll start out with the original integral of x to the nth e to the x dx. I can rewrite that as x to the nth times e to the x minus the integral of n times x to the n minus 1 times e to the x dx. And in fact, many times we'd pull that n out front of that integral, so I'll rewrite it there one last time. This is x to the nth e to the x, and then I'll pull the n, that constant, out front. N times the integral of x to the n minus 1 e to the x dx. So you can see there that I started out with an integral that involved x to the nth times e to the x, and now I'm able to rewrite this as an integral that involves x to the n minus 1 times e to the x, thus a reduction formula. I've reduced the power on my power function there. All right, so that's the idea behind a reduction formula. Here's one example of a reduction formula. Let's take a look at the reduction formulas that we're going to work with, though. I'll go ahead and show you all of them there. These are in your book there, and you definitely could use it to jot these down. These, by the way, are not something that you need to try to memorize. You just need to be able to use them. If I had the formula sitting in front of you of the reduction formula, I expect that you could use it to evaluate an integral of a power of a trig function. But let's go through them here real quick. The first one there is the integral of sine to the nth power of x dx. And that turns out to be equal to negative 1 over n sine to the n minus 1 of x times cosine of x, plus n minus 1 over n times the integral of sine to the n minus 2 of x dx. And that's for n greater than or equal to 2. So again, you can see that we started out with sine raised to the nth power, and we are able to rewrite this as sine to the n minus 2. So we've reduced the power on our trig function there. And eventually, if you use this property enough times, depending on what your original power is, we might have to use this a couple of times, like we've seen with rapid repeated integration by parts. You have to use it several times. Eventually, you'll get this down to either sine to the first power or sine to the 0 power. Anything to the 0 power, of course, is 1. So we'll eventually be able to integrate either just sine, because we just went through those rules at the beginning, or I'll end up with the integral of just dx, 1 times dx. All right, cosine. Cosine to the nth power of x dx is 1 over n, cosine to the n minus 1 of x times sine of x, plus n minus 1 over n times the integral of cosine to the n minus 2 of x dx. And that's, again, for n greater than or equal to 2. You can see the similarities between sine and cosine there. The only difference there is you're replacing, of course, sine with cosine. And the first term actually is the opposite. All right, still the second term is the same sign. All right, for tangent and cotangent, the integral of tangent to the nth power of x dx is equal to 1 over n minus 1 times tangent to the n minus 1 of x minus the integral of tangent to the n minus 2 of x dx. And that's for n greater than or equal to 2 again. For cotangent, again, if you replace the tangent with cotangent, and again, take the opposite of the first term here, that's the key on this, to get the pattern of what happens. This becomes a negative 1 over n minus 1, cotangent to the n minus 1 of x, minus the integral of cotangent to the n minus 2 of x dx. And that's, again, for n greater than or equal to 2. And then finally, for secant and cosecant, the integral of secant to the nth of x dx is equal to a 1 over n minus 1, secant to the n minus 2 of x, tangent of x, and then plus n minus 2 over n minus 1 times the integral of secant to the n minus 2 of x dx. And that's for n greater than or equal to 2. Again, if you jump down to cosecant, the only thing that's changed is that first term there has become the opposite, and we've replaced all the functions in there with their cofunctions. So negative 1 over n minus 1 cosecant to the n minus 2 of x, cotangent of x, plus n minus 2 over n minus 1 times the integral of cosecant to the n minus 2 of x dx for n greater than or equal to 2. So those, again, are your reduction formulas. Again, these are not something that you need to memorize. The only expectation that I have here for you is that you'll be able to use them. If I were to give you the formula and say integrate this power of a trig function, that you could use this formula to integrate it. In fact, that's what we're going to try next. Let's see if we can go through a couple of examples and actually do that. So let's take a look at example 3. They ask us to integrate cotangent to the fifth of x dx. All right, again, you don't need to derive the formula for this. You don't need to do the integration by parts. All you need to do is use the formula here. So the integral of cotangent to the fifth of x dx. So our n value is the 5. This is our value of n. All right, so when we go to use this formula, just remember that n is equal to 5. So our formula is, this is equal to, it's negative 1 over n minus 1. Let me put that negative back in there. Negative 1 over n minus 1. So n is 5, so that's going to be a negative 1/4. And then it's times the cotangent to the n minus 1. So that's going to be cotangent to the 4th of x. Again, we're just replacing n with 5 as we go through that formula. And then minus the integral of cotangent to the n minus 2. So that's going to be cotangent to the 3rd of x dx. So that's one iteration or one use of the reduction formula. But you can see I still have an integral of a power of a trig function here, still cotangent, that I still don't know how to integrate. So we use the reduction formula again on that part. So we're going to focus on just this integral and use the reduction formula in it. So the first part stays the same. We've got a negative 1/4 cotangent to the fourth of x. And then minus, I'm going to put this in parentheses so we don't lose that minus sign out there, and you definitely want to probably do the same thing there. But now our value of n is going to be equal to 3 when we use this. All right, so with n equal to 3, it's going to be a negative 1 over n minus 1, so that's going to be 3 minus 1 is negative 1/2, times the cotangent of n raised to the n minus 1 power, so that's cotangent squared of x. All right, and then we subtract the integral of cotangent to the n minus 2. So that's cotangent, instead of, or in place of the n, we're replacing it with 3. So 3 minus 2, that's cotangent to the first. I'll just leave it as cotangent of x dx. Again, you'll keep going with this process until you either get down to a power of 1, like we have here, or you have a power of 0. And in that case, you just have the integral of a constant. Here we've got to deal with the integral of cotangent still, but that's what we went through at the very beginning. We talked about the integrals of your 6 trig functions just to help us remember what they are. So you have a negative 1/4 cotangent to the fourth of x, and then it's going to distribute this minus sign through here, so it's a plus 1/2 cotangent squared of x. And then plus, now for the integral of cotangent of x. And again, the process that we talked about to help us remember this, remember that the derivative of cotangent is going to be a negative cosecant squared. We kind of use that to help us remember what the antiderivative is going to be. It involves the same trig function. So it's plus a negative natural log of the absolute value of cosecant of x, and then plus c at the end. All right, and I'll rewrite that one last time. I could have just made that negative there instead of plus adding a negative, but that's all right. I will just rewrite it here. Negative 1/4 cotangent to the fourth of x plus 1/2 cotangent squared of x minus the natural log of the absolute value of cosecant of x plus c. There we go. There's our antiderivative of cotangent to the 5th power. Again, if you were to take the derivative of this thing, it doesn't look very nice, but if I take the derivative of this answer, it all simplifies down to just cotangent to the 5th. All right, so let's take a look at one more example. This one's not in the book here, but we're going to integrate sine to the 4th of 3x. So this one is going to have an even power, first of all. So we'll see a little bit different procedure at the end. When it was an odd power, you eventually got down to a power of 1 on our trig function. Here we're going to eventually get down to a power of 0. But also notice that they've got a 3x in there. Now, to help us out here, I would suggest that you make that, or do a change of variables here. Make that a u substitution. That is u equals 3x, so that du is equal to 3 dx, or that means 1/3 du is equal to dx. And when we go to use the reduction formula, we just got to remember that we're going to write this in terms of u now instead of x and dx. But this becomes the integral of the sine to the 4th of u instead of 3x, and then the dx is 1/3 du. In fact, I'm going to pull the 1/3 out front, so you have 1/3 the integral of sine to the 4th of u du. Okay, so this is equal to, then, now we're ready to use the reduction formula. Actually, I'm going to write this down below here. This is equal to, the 1/3 stays out front. I'm using the reduction formula again only on the integral. That's all I use it on. So the 1/3 stays out front here. I'll put a parenthesis here so I distribute that 1/3 through at the end. But now let's deal with the sine to the 4th of u. So sine to the nth of u is equal to a negative 1 over n. So it's going to be a negative 1 over 4. Again, n is equal to 4 here for us. Times the sine to the n minus 1. So that's going to be sine to the 3rd of x times the cosine of x. All right, and then we add on n minus 1 over n. So that's going to be 3 over 4. And then it's the integral of sine to the n minus 2. So that's going to be sine squared of u. And I did that. I said I got to remember that it's in terms of u, and I wrote it down in terms of x. So I'm going to go back and fix that. These should be sine cubed of u and cosine of u. That's easy to do. Remember, if you do a change of variables, you got to keep this in terms of the same variable that you've changed it to. All right, so it's sine squared of u, and of course times du at the end. All right, so now I have it in terms of sines, the integral of sine squared, and so again, I'm going to use the reduction formula just on this guy right here the next time. So let's do that. I'm going to distribute the 1/3 through here just so I can simplify as I go. So I'll have a negative 1/12. It'll be sine cubed of, I want to write that as an x. It's a u though. Sine cubed of u times the cosine of u plus 1/3 times 3/4. The 3's will cancel out and leave you just 1/4. And again, now I'm replacing the sine squared, the integral of sine squared, with another iteration here of this reduction formula. So according to the reduction formula, we get a negative 1 over n. Now again, n is equal to 2 this time. So it's going to be a negative 1 over 2, negative 1/2, times the sine to the n minus 1, which 2 minus 1 is going to just be 1, so we don't need to put a power on that, of u, not x, times the cosine of u, and then plus, it's n minus 1 over n, so that's going to be 1 divided by 2, times the integral of sine to the n minus 2. So n was 2, so it's sine to the 0. I'll go ahead and write it that way here. It's going to be sine to the 0 of u du. All right. Let's rewrite this one last time here. We have a negative 1/12 sine cubed of u. Cosine of u, I guess I do have to rewrite it again because I got to get back in terms of x here before I'm done. And then distribute the 1/4 all the way through these parentheses, so it's going to be a minus 1/8 sine of u, cosine of u, and then plus 1/8. And then it's the integral of sine to the 0. Again, anything to the 0 power is 1, so the antiderivative of 1 is just your variable. So this is the differential of u we've got in there, so our variable is u. So again, if it gets down to the 0 power, that's nice. I don't have to remember the rules for my integrals of trig functions. And then, of course, we have a plus c at the end. And then finally, the last step of this is to replace u with what it was equal to. Let me just scroll back up so you can refresh your memory there. Remember, u is equal to 3x. We're going to replace u with 3x. So it's a negative 1/12 sine cubed of 3x cosine of 3x minus 1/8 sine of 3x cosine of 3x plus 1/8 times 3x. I guess you could write that as 3/8 x if you want to write it that way, plus c. So realize that even if it has something besides an x there that you're taking the sine of or cosine, whatever your trig function might be, realize that you can just do a trig substitution, or excuse me, a variable substitution there, replacing u with the 3x, and be able to still evaluate that using your reduction formula. The key is at the very end, make sure you go back and plug in what u is equal to. All right, that's as far as we're going here in this section.